Hello everyone, in this video I'm going to be talking about solubility equilibria. We generally assume that ionic solids dissociate completely into separate hydrated cations and anions. So for the example of calcium fluoride, I would expect one calcium ion and two fluoride ions to come out of the solution. However, as the concentration of Ca2 plus and F minus increases, the possibility of these ions colliding to reform the solid phase increases as well. So we have a forward and a reverse reaction in competition. So when equilibrium is reached, no more solid is able to dissolve, and so the solution is said to be saturated. So there's a common misconception between solubility and solubility product. So solubility is an equilibrium position. It is a concentration of maximum saturation. So this position may be affected by the presence of a common ion solution, by the temperature, things like that. So for silver chloride, we could have a solubility of 1.33 times 10 to the negative fifth molar. Now, say it's in solution with HCl, which has a common ion, that chlorine, it might be 2.5 times 10 to the negative 6 molar. On the other hand, solubility product is an equilibrium constant. It is Ksp. There's only one value of Ksp for a given solid at a given temperature. So for silver chloride, its solubility product is 1.76 times 10 to the negative 10th at 25 degrees Celsius. So the first type of problem you're going to come across is calculating Ksp from solubility. So copper 1 bromide has a measured solubility of 2 times 10 to the negative fourth molar at 25 degrees Celsius. Calculate its Ksp value. What's great about solubility equilibria is the fact that your reactant is a solid, which means that you don't actually care about anything from the actual copper 1 bromide. So assuming you're throwing this in solution, your initial conditions of your ions are both 0. So you're going to dissociate to create those, so both of these are going to be X. Right? So what they actually end up being, right, what that X is your solubility, 2 times 10 to the negative fourth molar. So each of these is 2 times 10 to the negative fourth, 2 times 10 to the negative fourth. Now when you go to write your solubility product expression, right, you've got your copper ion times your bromine ion, and there's nothing in the denominator because all of your reactants are solid, right? And solids are not included in equilibrium expressions. Right? So in this case, the Ksp is going to be equal to 2 times 10 to the negative fourth squared. So my Ksp is 4.0 times 10 to the negative eighth, and that is my answer. This is another example calculating Ksp from solubility, but slightly different. So lead 2 bromide has a measured solubility of 0.010 molar at 25 degrees Celsius. Calculate its Ksp. Again, because that lead bromide is solid, don't care about that at all. So I'm starting with none of this original amount, but here my lead is X, okay, but my bromine is actually going to be 2X. Right? So when I go to write my Ksp, right, I end up having the concentration of the lead and then the concentration of the bromine squared. Right? So this idea, you have X and then you have 2X squared. So your overall is going to be 4X cubed. So the X in this case you're getting from the solubility. So it is 0.010, right? That's what's in each of these. It'll be easier if I just plug it straight in. So 4 times 0.010 cubed, that is 4 times 10 to the negative sixth. This next problem is slightly different. We're going to be calculating solubility from Ksp. In other words, we're solving for X. So the Ksp for copper 2 iodate is 1.4 times 10 to the negative seventh at 25 degrees Celsius. Calculate the solubility at 25 degrees Celsius. So I don't care about this guy. What I know is I'm starting with 0 and 0. I'm adding X, adding 2X. So that's X and 2X. When I write my Ksp, it is the copper ion to the first. It is the iodate ion squared. Right? So here I've got X and then 2X squared. So once again, this is equal to 4X cubed. Right? And I know my Ksp is 1.4 times 10 to the negative 7. So here all I'm doing is solving for X, which is 3.3 times 10 to the negative third. This does need units. It's solubility, so it's concentration, M. So the common ion effect alters the solubility of a solid in the same way it decreases the percent ionization of an acid or a base. If one of the ions dissociating is already present in the solution, the solubility of the compound will decrease. So for silver chloride, if I already have sodium chloride in solution, I'm not going to be able to dissociate as much. Similarly, if I have silver nitrate with that silver common ion, I won't be able to dissociate as much in solution either. So we're going to see how that is also going to affect solubility. Now, probably the most common type of problem you're going to see with solubility equilibria is asking, if I mix these two things, will a precipitate form? Remember, a precipitate is a solid that forms in solution from a chemical reaction. So this says a solution is prepared by mixing 150 milliliters of 0.01 molar magnesium nitrate and 250 milliliters of 0.1 molar sodium fluoride. Determine if a precipitate of solid magnesium fluoride will form, and it gives you the KSP of that magnesium fluoride. This entire problem is going to be based on comparing K and Q. You need to know where you are, right, in terms of your initial concentration so that you can compare which direction is equilibrium going to lie. Right? So we're talking about magnesium fluoride, right? Magnesium fluoride dissociates into two ions, right? There's a magnesium 2 plus, and then there's two of the fluoride ions, right? So, where am I getting magnesium from? I'm getting magnesium from the magnesium nitrate. Right? So, this is going to involve a dilution problem because I'm no longer that magnesium nitrate on its own. I'm combining it with another solution of sodium fluoride. So, my concentration of magnesium ions, right, in the total volume, so 150 plus 250 in my total 400 milliliters, right? I need to know that concentration. It's going to be equal, right, to the concentration from the 0.01 molar magnesium nitrate in 150 milliliters. Right? So that means that my magnesium is equal to 3.75 times 10 to the negative third molar. All right, so now I need to look at my source of fluoride ions in that same 400 milliliters. Okay, that is going to come from my sodium fluoride. So I got 0.1 molar in 250 milliliters. That means that my concentration of F minus is 6.25 times 10 to the negative second molar. All right, so Q. Q is written the same way that K is, right? It is the concentration of the magnesium and then the concentration of the fluoride squared. Remember, I'm not including magnesium fluoride because that's a solid. So the magnesium I found was 3.75 times 10 to the negative third. Fluorine was 6.25 times 10 to the negative second, and that is squared. So my Q is 1.46 times 10 to the negative fifth. Right? So in this case, my KSP, which was 6.4 times 10 to the negative ninth, it is smaller than my Q. Right? This means that I am going to the left. Right? So I am going to be reforming this magnesium F2. Now, that is the solid in solution. So yes, a precipitate will form. That solid has been formed. Right? If K was greater than Q, no, a precipitate would not form. It would stay as its ions. It would be shifting right. But because it's shifting left to reform the solid, precipitate is formed.